Halo oil fans! This video is a tutorial for a free open source CAD program called SolveSpace. CAD stands for Computer Aided Design, but it's part of an even more complicated acronym, CAD-CAM, which stands for Computer Aided Design and Manufacturing. In the modern world, pretty much everything is designed with the help of a computer before being built with the help of a computer. So people planning to stay current in engineering and related fields should really learn computer design methods. SolveSpace is free and open source, and it's a first-rate program. I recommend it for many reasons. I've always advocated open source, and many alternative CAD programs are no longer free or are gradually becoming impossible to use. As just one example, Fusion 360 is becoming more restricted as AutoCAD tries to get people to sign up for their paid version. Similar programs are doing the same. FreeCAD is an open source CAD program sort of like SolveSpace, but in my experience, as the years go by, it's becoming buggier and harder to use. I tried creating one of this tutorial's example projects in FreeCAD, but there are now too many non-working or disabled features to allow this, and I gave up. Even when it's working, FreeCAD is difficult to use. It has an unintuitive user interface bordering on the mystical, and from time to time it will wrongly announce that your project files are from an earlier FreeCAD version and offer to convert them, and regardless of whether you agree or disagree, will eat the files, render them unreadable, and force you to start over. But to me personally, the most irritating FreeCAD feature is the inability to tell you why a project is broken. A typical FreeCAD error message is, quote, "Read the message in the log window," unquote, which is printed in the log window. Enough said. After years of experience, I can only unrecommend FreeCAD. That's why this video is about SolveSpace, which was written by people who fix old bugs before creating new ones. Be sure to check out the links in this video's description, one of which is my SolveSpace article that includes files for this video's content. This is a hands-on SolveSpace tutorial, starting with the user interface and proceeding step by step through some demonstration projects. So, let's get started. Here's the SolveSpace sketch drawing display. This dotted line surrounds a plane, which in this drawing at least lies on the XY plane. Think of this plane as a sketch pad lying on a desktop, a horizontal pad. Remember that SolveSpace sketches are two-dimensional, which are then extended into 3 dimensions using various extrusion commands, which are right over here. Okay, big toolbar over here. The top section of the toolbar are drawing commands, lines, squares, circles, and so forth, that are applied to your two-dimensional sketch. Next, we see a whole bunch of constraint applying commands, which tell you, which you use to describe the lengths, arcs, and angles, so forth, of your drawing. The lower section is, as I said before, this is the area that has the extrusion commands that take your 2D sketch and turn it into a 3D object. The property browser over here, a whole bunch of commands across the top that control the visibility of various things, and an outline of the project, which has just 2 entries right now. Each new 2D sketch and each new extrusion into 3D gets another entry in this list. See this expression DOF? That refers to degrees of freedom, and that has to do with constraints. If I make a square like this, it has 4 degrees of freedom, which means it's out of control, basically. And in a later tutorial, I'll show how to apply these constraints so that the number of degrees of freedom is 0, which is what you want. At the moment, you can do pretty much anything you want. You can control this and move it around, obviously not a very useful drawing if it doesn't have any definitions within it. And so the constraint process is how you turn a 2D drawing into something reliable and consistent. And you always want the DOF to be 0 is the ultimate goal. Okay. This may seem like a lot of information to absorb, but don't despair. SolveSpace is a pretty hand-holdy program compared to FreeCAD and other environments. And SolveSpace's learning curve is much easier to ascend than most of the others. Also, the basic ideas you learn in SolveSpace can be applied to FreeCAD and other environments later on. Okay, let's make a 2D sketch, constrain it, then extend it into 3D. Not necessarily in that order. I'm going to press keyboard R, which I know is, let's see, sketch rectangle, to create a rectangle. I'm going to use my mouse to actually make the rectangle. Oops. So we have a rectangle with 4 degrees of freedom, which are things that aren't defined, like its position and the lengths of these sides are all undefined. So just for fun, I'm going to remove this constraint here, this H, which forces this line to be horizontal. So I'm going to take that away and see what happens. Okay, it's no longer forced to be horizontal. I'm going to just for the fun of it, I'm going to select these and delete them. Now we have 8 degrees of freedom. Pretty much anything goes. Now I'm going to add some constraints back. This one I'm going to make vertical. And this one here, vertical. This one horizontal. Oops. Wrong move. And this one horizontal. So now we're back to 4 degrees of freedom. Just for fun, I'm going to say this is a dimension, D, of 80 millimeters. And I'm going to say this side and this side are the same, for which I press Q. Now, these two sides have a common, see the little horizontal and vertical lines, which I've now marked red. They refer to the fact that this and these two sides are equal in length. Okay, but we still have 2 degrees of freedom, which means this square can move around in space. So just for fun, I'm going to make this and this point symmetrical about the vertical axis. And the symmetrical shortcut key is Y. Having done that, I now have a situation where there are more than enough constraints. And what that means is that this constraint that says this line is horizontal is in addition to another constraint that also forces it to be horizontal. So I have more than enough constraints. So let me go to this list over here and click the mouse, which causes this H to become red, and I'll just press the delete key to delete it. Now we're back to normal again. Now notice about the square that it's still moving in the vertical axis, but can no longer move in the horizontal axis because of the constraint that I've applied. Now let me apply the same constraint here. Press Y for symmetrical. And again, we have a redundant constraint. One more constraint than required. So let me click the vertical listing and press delete. Now we have a fully constrained square. See, it says OK where there was some numbers originally. So we now have a fully constrained object. Now the fun part. Now we're going to go extend this 2D sketch into 3 dimensions. By the way, when I rotated the plane, I was using the middle mouse button. I was holding down the middle mouse button to create that effect. which I regret already. Anyway, now I'm going to extend this 2D sketch into 3D, and I'm going to choose this particular extrusion. And the shortcut key happens to be Shift+X. So here goes, Shift+X. Ta-da! We now have a three-dimensional object from a two-dimensional sketch. And the property list shows a new item which refers to this extension, this extrusion in two-dimensional, from two to three-dimensional space. And there's one degree of freedom. And that degree of freedom is the fact that we haven't defined a size for this extrusion. In fact, by dragging the mouse, I can make it any size I like. So the first thing I want to do is enter the extrusion menu, and I've decided to make this two-sided. See how it says one-sided? This is what it looks like two-sided. It's symmetrical about this plane, which is the original XY plane that I'm highlighting right now. And so one-sided means that it can be extended one side or the other. Two-sided forces it to be symmetrical about the plane that originated from. So let me just go back here like this and make this two-sided. And let's define its depth. So let's press D for dimension, and let's make it 40 millimeters thick. Symmetrical about the XY plane. To prove that, I'll see. Okay. Now, let's add another drawing to this list. And rather than draw another square, I'm going to just copy this one. I'm going to just select the entire square by dragging the mouse and pressing Control-C for copy. Now I have a copy. And now I'm going to go out here and select this plane and create a new sketch, which is Shift+W, creates a new sketch. Now I'm going to say paste the square that I copied from the original drawing into this new drawing. And let's see, I think I'll make this one smaller. I'll make this 60. Oops, all the things that I did before haven't been brought over. I'm going to make this, and this all equivalent. Now the next thing I want to do is make this one symmetrical about the axes as I did in the original sketch. So I'm going to select these two positions, these 2 points, and this axis, and press Y for symmetrical. And remove a redundant constraint. And I'm going to select this axis, this plane, and these 2 points to make them symmetrical about that axis. Same effect. I've created an excessive number of constraints. Now I have a fully constrained 2D drawing, which I'm going to also extend into 3 dimensions, like so, and make it a little longer, and make it some two-sided. Now the reason for this exercise, creating 2 solid objects, is to show a special property of these objects. Now notice that this solid model is a union, which is a Boolean algebra term to refer to the fact that the displayed object represents a union of the 2 original objects. But if I say a difference and remove all these extra lines to make something visible, I have drilled a hole through one rectangular object with another one. Let me put these lines all back. And you can sort of see from here, even though all the lines of the drawing lines are all present, that I've drilled a hole through the original object by selecting difference. And so what remains is the difference between the two objects, which is what we have. And there's other options, of course. Here's an intersection, which means what remains as an object is where the two solid objects intersect. Definitely play with these options when you get a chance to practice. Here's the difference, which is the only parts remaining are how the two objects differ from each other, and this one, which is in some sense the opposite, it's how the two objects intersect. And just for fun, I'm going to remove all these extra lines. And that's the intersection of the two right there. And if I do this, now I have only the difference between the two objects. Let me just put all these lines back out and do non-display. Okay, now let's examine some other extrusion commands, these two in particular, right here. See how they work. Here's an example. Let's make a cup, and let's use a pretty efficient way to make a cup that relies on the knowledge that we're going to use these commands. I'm going to just start by making the side of the cup, and the bottom. Real crude at the moment, and with 5 degrees of freedom. Well, let's start here and make a thickness of 3 millimeters for the bottom of the cup. And I want the side of the cup and the bottom of the cup to have the same diameter, thickness. So I'll just make these two equal. I'll select both of them and press Q for equal. And I think this needs to be horizontal. Each time I make a change, you'll see the number of degrees of freedom goes down. Let's make the diameter of the cup 40 millimeters and the height 80. Where are we at? Okay, we have no degrees of freedom. Now, just for the fun of it, I'm going to perform this so-called rotation. By the way, these two names are confusing. One of them's called a rotation, and the other one's called a revolve. And those are basically synonyms, but they actually do have different meanings in this program. You just have to remember how they differ by their position on the toolbar. So here goes, we're going to do this one. And what this one does is it always rotates through 360 degrees. But in order to use it, I have to specify an axis for the rotation, which I'm doing right now. Now we've established an axis right there. And that's the rotation. Pretty crude cup, right? So now we've done that. We've created our model. Now let's improve the quality of the drawing. First, I'd like to make this top rounded. So I'm going to take this and I'm going to press G. Now what G does is it converts an active part of the sketch, which is a white line, to a construction line, which is green. Now a construction line is used to provide a reference in a sketch, but it doesn't actually become part of the sketch. So now we have a gap in our drawing. SolveSpace expects an outline in a sketch to be complete, to not have any gaps. And at the moment we have a gap. So I'm going to choose this arc command, which I'll use the keyboard instead. I'll just say A for arc. And then go right here and create the arc. And I'm going to make this tangent. Oops. I have to select two things for a tangent. And what is that code? Oh yeah, L. I'll use the keyboard. L for tangent. Same here. And now we have a redundant constraint. So let's remove that. Okay, now we have, what do we have as far as... nevertheless, this is an improvement. Let's take a look at it. The top of the cup looks better, but the bottom is still a straight line. So let's play with that a little bit. So let's go down here. And I would like this to be a curve. And so I just selected a point. And this one here, which is called tangent arc, Shift+A, does this. It creates a tangent arc. It creates two new points and draws an arc between them. I'm going to do the same thing here. Now, because I want this cup to have a certain appearance, I'm going to make these two, which are the center of the arcs, I'm going to make them the same point in space. And we'll get rid of a redundant constraint. Now, if I go like this, with this point, I can choose the profile that I like just based on aesthetics. So that one looks pretty good. So let me click this arc here and press D for dimension and say, basically turn that into a definition. Now, here's something about the radii of circles and of arcs. Now, see this indication? There's a little circle with a slash through it. That refers to a diameter. So it's a diameter of 10 millimeters. But if I select this and go up here into the menu that appears and select choose radius, that's more to my liking. It also, in a complex technical drawing, you're in general better off using radii than diameters. Anyway, so now I have this as an outcome. So I have a nice curved bottom. All right, now, because this is an exercise about various ways of doing revolutions, I'm going to delete this. And instead, I'm going to use the lower one, which is called Revolve. Gee, how informative. Which is Shift+V. So Shift+V, oops, same reason I have to select an arc for my revolution. And I'm going to do Shift+V again. Now, this command here that I'm pointing at differs from this one. This one, the upper of the two of them, always goes through 360 degrees. This one, the user chooses the angle of revolution. So, at the moment, it's like 120 degrees or thereabouts. So, and also, you may notice that there's 1 degree of freedom, which is an undefined angle, which is this angle right here. So at this point, I need to select an angle. So I'll select this line and this line, and I'll do it correctly this time, and press N for angle. And the default is 120 degrees. Let's just put in 90 for the fun of it. Oh, another thing that I failed to demonstrate, let me just delete this for the moment, is you can crank this manually around to whatever desired angle you want. And then having done so, you then can press N, select two sides, press N, and get the angle, specify the angle. So I'm going to say 45 degrees. By the way, let me, as long as we're on this topic, this says what the angle is. But if I click this box over here, if I select the angle constraint and then click this box, this becomes a reference, which means that it describes what the current angle is, but allows the user to change it. Remember that a reference only describes. A definition prescribes. So if I unclick reference, this is now a definition, and it's no longer under the user's control, and the degree of freedom, the last degree of freedom disappears. But you can always change an angle numerically by double-clicking the current reading. So let's say 90 here. Okay, so we have looked at two ways of making a cup. And just for fun, I'm going to delete this one. And I'm going to go back to this drawing and use the full revolution. Again, I have to specify what the axis of revolution is. And do this. Now, for the fun of it, just to add to this exercise, it doesn't have directly to do with extrusions, although it does have an extrusion in it. I'm going to go back to here. Now what I'm going to do is make a handle. And here's how I'm going to do that. First, I'm going to go back here. I'm going to select that. And I'm going to create a new sketch. Shift+W. Whoops. Oh, I see what the problem is. I have to select. What I'm actually selecting is this plane right here for the sketch. So there. Okay. Now I'm going to make a handle. Oops. Two separate lines. To start a new line without using the toolbar button, press S. I hope I don't have a, oh, I do. There is one in there. The SolveSpace has the nasty habit of creating an extra line at the end of each line. Not so great. Now I know what this I'm after here is I want these to be the same length, and side by side they're going to be the main body of the handle. So let's say H on this, make them side by side, and this, and let's say what we want this to be. Oops, has to be points. Whatever, I'm going to say 8. 8 will be fine. Now, I want to draw a couple of arcs. So I'll start right here. I definitely have an issue. I want to show all. And this here. I'm manipulating the controls that govern the visibility. My plan is to have these two lines be the body of the handle. Actually, you know what? I think I'll copy these and put these over here, which I have another use for them over here. And I'm going to join these together with arcs, like so. By the way, what is that arc? Keyboard shortcut is A for arc. It'll be handy. And I want this to be horizontal. Vertical, vertical. And I'm going to get into trouble with how wide this is, so let me specify a dimension here of 6. And and these two should be the same origin. O for origin. And let me select a height for the vertical part of the handle. Oh, that's fine. And we still have 2 degrees of freedom, and I don't know why. Oh, I know why. It's because this is floating in air. So let's say height above the horizontal axis, a dimension. Let's just arbitrarily accept the default there, and the distance away from the central axis. Same idea. 40, 48, whatever. And now the fun part. See where the handle is located with respect to the cup? We want to use one of the earlier controls, this one here, to create a thickness for it. And we want it to be two-sided, and we want its dimension to be diminished. Actually, why don't I just select it and choose a diameter of 8. Now, everything looks pretty good, all except for the part where it's sticking out in the inside. And if I make a solid model of it, which just for the sake of visibility, I'm going to hide everything and show that, in fact, it's sticking out through the inside. So I have some choices here. First, the handle's thickness is greater than the thickness of the cup, so obviously it's going to stick through. So I'll go back to the normal way of looking at things with maximum visibility. And first I'm going to make this only to make sure that this part here is sunk into the, let me see what I'm not explaining this very well. I want the handle to disappear inside the side of the cup. Now as to this one, this is a bit more complicated. I've got the handle is sticking through the inside of the cup. So I know how I'm going to deal with this. I'm going to make a new drawing. And this drawing is going to consist of a simple let's see, that looks pretty good. Now I want this to be lie on that axis there. I want this one to be equal to that. So it brushes the inside of the... No, huh? Oh, I see what I did wrong. I have to select 2 points. Okay. No, I can't do that. I have to... Oh, duh. I can just select the line. All right. Now we need to specify a height. Whatever, 64 is fine. And we have 1 degree of freedom. Oh, I see what's wrong. We just specify this dimension. 10's fine. Now we have 0 degrees of freedom. So now I can create a 360 degree rotation, which I always forget to do this part. Where's the... Oh, I see what I can just do it this way. I have to specify an axis for the rotation, which apparently I haven't done yet. Oh, I'll do it this way. Okay. Now we have the inside of the... Okay, a little side digression here. All these red marks indicate that there's some conflicts within the drawing where surfaces are colliding with each other. Now the remedy in SolveSpace, the general remedy, is to select the first drawing of the outline. And see this item here says force NURBS to triangle mesh. I won't try to explain what that does, but it does solve the problem. Now, what I want this to do is not add to the Oh yeah, this is a good time for an example. Let me just close this off and hide all this. Now see what I've created. I've created the cylinder inside. But what I want to do is subtract that, which subtracts itself and the part of the handle that's sticking inside. Let's see what intersection does. Ooh, cute. That's the part that it's removing right there. This is the union, which is the addition of everything to everything else. This is the difference, which is what we end up wanting. We'd like to just remove that part of the handle. And this is the intersection where they come together, which is, this actually shows the part that we're removing from the handle. So now we have a cup. By the way, there are a number of much fancier ways to create a cup handle with rounded sides, which I'll have to show in a more advanced video. This is still a beginner's guide. So I have the very, very easy handle to make. Anyway, the point I'm making here is that the user has plenty of latitude. By the way, from a 3D printing perspective, this gap between here and the horizontal plane will cause problems. And there's a solution for that which I'll describe in a later video. Anyway, we have a cup. And let's just hide all the lines and show the cup. There are two more extrusion commands to cover. These can be used to create duplicates of either sketches or previously created 3D extrusions. One of the commands creates a linear array of duplicates. The other creates duplicates on a chosen rotation axis. And they're right here, these two. This is the rotation axis command, and this is the linear command. First I'll create a little platform, a little holder for this exercise. What the heck? Let's say 80 and make them all the same. Q for equal. And that's wrong. Just delete this and this. And let's make it centered across the, oops, using a symmetrical. And symmetrical this way. Okay, so we have a fully constrained silly platform. Now first I want to extrude it, which I do now, and I'll just say this is some appropriate, whatever, 8. So I have like a platform. Now, let's go create a new sketch. For an example. Let's just make a little circle. And the first command I'm going to try is the rotational command, this one. So I just created 2 duplicates, total of 3, of my little circle I created. And I have the option, I'm right now in the menu for this particular command, and I can change this to any number I want. Let's say that that's what we want, like that. Now having done that, let's try extending it with a command we've covered already that extrudes out in a linear fashion. That's pretty slick. So let's go back to here, where this is the one that did the rotation. And this one is the original. Now let's try the other command, which creates a linear array, which the user gets to manipulate. And again, the default is 3. Let's change that. Let's go crazy and use 9. That's a lot of little circles. And this can also have modifiers be placed on it as well. So let's see if we can put all these into the original size of the... To do that, I need to make this smaller. I'm going to make it 2. Go back up here to extrude. This is the one I want. I want to go to translate and select a member. And I can just create a dimension here. And go back to the extrusion. I'm not too crazy about that height. And just to make this look completely ridiculous, I'll hide everything except the extrude. That's the one I want right there. And this one. So those are my 2 examples. There's one more extrusion command that's somewhat exotic and very useful for advanced modeling. It's called the Helix. It draws a spiral extrusion of the sketch applied to it. But since a picture is supposedly worth 1,000 words, let me show you. First, let's make a hexagonal bolt head. I have an efficient way to create a hexagon, all sides equal in length. Here we go. C for circle. Circle. Let's make that a construction circle, and let's set a diameter of whatever, 20 for the moment. But what I'm after here is I want this to be a radius, and I have a particular value in mind, so I'm going to type that in. When I make machine bolts, I consult online resources to figure out what the dimensions are. Now I'm going to make 6 lines. I'm going to press keyboard S for each line segment. Press S again. Okay, we have 6 lines. I'm going to get rid of this redundant horizontal. And we have 5 degrees of freedom. So let me just select all 6 line segments. Realize that all these line segments are pinned to the circle. So if I make them all the same length, they will automatically become an exact hexagon. Now let's extrude this along the z-axis with this option here. And let's set a height of 6.5 millimeters. Again, I've looked up most of these numbers and I have a pretty clear idea of which numbers to use. Now I'm going to create a central cylinder for the bolt that's going to include some important measurements, useful later. And again, I have a clear idea of what dimensions I want. And this one is sort of arbitrary. I'll just make it 24 millimeters tall. Okay, now let's complete the central cylinder by making it cylindrical. Like so. That's going to be the basis for our bolt. And by the way, this particular sketch and extrusion contains two important measurements, the overall height and the radius, both of which are used later on. This is how one can use prior entries, dimension entries in SolveSpace. You can refer to earlier entries to avoid making multiple entries of the same dimensions. Very bad idea. Now probably the most important single part is the thread prototype, which I'll get started here, a new sketch, and come over here and make some lines. Make this one vertical and make them all the same size. And this dimension here has to be exactly. The reason for this is that the thread pitch, which I'll be entering in a bit, is 1.5 millimeters. And in order to keep the helix from colliding with itself, this has to be a slightly smaller value. That's the reason for that oddball entry. Now this one, let's see, make sure we know where I am. Yeah, that's where I am. So I'm going to go here. And I want to say, there's a reason for this. I won't try to explain it right now, but the thread prototype has to be a bit away from the central cylinder to avoid some conflicts. And this can be equal to this. All right. We're about to create the actual helix. And what this does is, this thread prototype is going to be wound around this central cylinder as many times as desired. So let's just select an axis for this operation. And this often happens. The helix went in the wrong direction. And the remedy is to just take the mouse and drag the initial helix and the other onto the other side. And also I have this in mind. I want to have a certain dimension here. So I'll specify that. And now the most important part. There's a central idea in thread design called thread pitch. As it happens, SolveSpace uses the same terminology. And I happen to know that the thread pitch I want is 1.5 millimeters. So I'll just enter that. And as you can see, it responded by creating a machine thread. A pretty good one, actually. One more exotic feature, one of my favorites. It has the effect of creating a taper at the top of the bolt and a rounded edge down here. Pretty slick. Here we go. First, I've got to create a new sketch. Shift+W. Get things centered. And create a series of lines. Press S to continue from here. As you can see, I've used the previously entered height of the central cylinder as one of the dimensions. This I want a particular angle, particularly important. And one last little glitch, one last little change. I want a tangent arc right here, and I want it to be 3 millimeters. This sketch also gets swept through 360 degrees, like so. And what's interesting is that it creates a solid cylinder because of the selections. Now, it's set at union right now. What I want is intersection. If I select intersection, only the parts that the original bolt and this addition have in common, that they intersect, creates the outcome. And this is a pretty nice outcome, actually. Pretty good result. Let me hide these other lines. And you can see that there's a nice taper at the top, and there's some nice curved surfaces on each of the apexes of the hexagon on the bottom, all created by this outline right here. Pretty nice. Now to export this SolveSpace project. The best export choice is a file compatible with 3D printing like STL, which stands for stereolithography. Here we go. Export triangle mesh. The default choice is STL. If it isn't displayed, make sure it is, and save. There might be some error messages like this. They can usually be ignored. The STL file format is fairly universal, but remember, it only exports the 3D appearance of a project, not its details. Only SolveSpace project files contain that information, so always remember to save SolveSpace projects in their native format, which I'm doing now. That's section 5. An STL export file can be used by a 3D printing slicer program like the popular Prusa Slicer. Let's load this into this program. Import STL. And slice. Now we have a sliced project ready to print. I'm going to go on, scan through here, see what it looks like. Let me just do this and this. Looking good. 18 minutes. So, ready to print. Here's the bolt project in the Blender graphics program, threaded onto another SolveSpace project not covered here. I always like to import my SolveSpace projects into a Blender environment because they always look better here than anywhere else, including reality. I improved the previously described cup design. I made a more usable handle, but in a complex way not appropriate to a tutorial. The SolveSpace source for this project is on my website article linked in the description. I'm just showing some of the details here. More civilized handle. When I printed the final cup design, I took advantage of a new Prusa Slicer feature called Organic Supports. It looks like this in the slicer. The organic support feature is a big improvement over older support methods. It's being adopted by many other slicer programs because Prusa Slicer is open source. Here's where it's located in the menus right here. Under print settings, support material. Pretty amazing stuff. In this case, it allowed me to create a 3D print design with overhangs that wouldn't have been possible with the older methods. I'm very impressed by this feature. Here's the tutorial bolt design in a Blender animation showing how it would work with massing threads in a metal plate. As I said before, I like seeing my designs in Blender where everything is unrealistically perfect. Well, I guess that wraps up this tutorial. Please leave a comment if I've left anything unclear or if you'd like to see any SolveSpace features explained in more detail. Please like and subscribe, and thanks for watching.